Hello friends, welcome back to the class 2 lecture, the continuation of finite element analysis and its applicability to aerospace structures. So we have been speaking on the finite element basics theory and slowly moving into the FEA applicability to aerospace structures. I have been speaking on the job of the stress analyst, what kind of challenges would be there and what you have to model and what you have to consider before doing a finite element analysis, and what you can expect and what are all the assumptions you have to make. So now slowly moving on to the applicability of it on the aerospace structures. So there are certain things that and the FE analyst needs to keep in mind. So the things that needs to be considered in mind on the first and foremost is the generic modeling philosophy of finite element analysis. So whenever you model a geometry, whenever the structure is modeled within the finite element tool, so you have to come up with the meshing. So in order to mesh, you need the geometry, and whenever the geometry is supplied, and you have to decide whether the meshing, the elements should be meshed on the outer mold line, or it's on the inner mold line, or it's in the mid plane of the geometry. Most aerospace structures on the skin panels, on the wing skin panels, on the fuselage skin panels, or the thin structures, they are mostly modeled at the mid plane of the geometry. To demonstrate this, I will be switching into paintbrush. So suppose, so you have a skin panel which is something like this, of certain thickness, and then when this geometry is imported into the pattern, and what you have to do is you have to extract the mid surface, and then you have to mesh the geometry. And sometimes what happens, on some instances you might be required to mesh the geometry on the outer mold line, which is OML, which is called outer mold line, which is the outside surface, or sometimes on the inner mold line, IML, which is the inner surface. So based on whatever you select or the user selects based on the engineering judgment, so you have to be really careful with the modeling philosophy in terms of assigning the offset. Whenever the mesh is done on either OML or IML, you need to specify the element offset so that it exactly captures the boundary. And then the second one is the idealization of the structure. So you see, when a real structure is idealized into the mathematical model, we should have a backup calculations in for the geometric parameters in order to accurately represent the stiffness of the real structure into the mathematical world. So one sh- uh, one should have a real backup of the calculations to prove that the stiffness of the real structure is more or less reasonably or closely represented into the mathematical tool in order to achieve the accurate results. So another thing, the third point would be the load paths within the aerospace structures, aircraft structures. So one has to be aware of the critical load paths. So how the load, what are all the members of the structures that take most of the load, and what doesn't take load. or which is a non-structural panel. Suppose on the fuselage you can see small access holes or access panels. Access panels are non-structural panel, so it depends on what you should model within the tool and what you shouldn't. You should have a very clear understanding. And finally, the interface points. The FE analyst in the aerospace sector, they should really have the capability to understand the connection points, which is the interface points, where how the structure is attached and where it is attached and how to model the connection points within FEM. So those all things we will discuss probably in detail as we go along the course. I'll be showing you various examples and various speaking to you on various design aspects to discuss the things. So let's start discussing the modeling philosophy first. So first and foremost would be the aircraft skin. The skin panels are very thin structures or thin membrane structures that takes most of the in-plane axial stresses and in-plane shear stresses. So those skin panels are modeled using 2D elements, preferably quad elements, quadrilateral elements, and then the 1D stringers and longerons, which are modeled using 1D elements, mostly rod elements, because they take only the axial force, they have only the axial capability. And then moving to the spars and ribs. Spars and ribs are more or less like beams, so that will have both flanges and webs. So in a very global model, sometimes the entire spar may be idealized as one rod element or one bar element using a 1D element. So or sometimes it might be a combination of 1D and 2D. Sometimes it is like 1D for the flanges and 2D for the web alone, or sometimes it might be a combination of 2D like flange, and the interconnection between the flange and web will be 1D, and the web is 2D, and then again flange is 2D with the interconnection modeled as 1D. So whatever may be the decision from the FE analyst, how to accurately capture the stiffness to of the real structure into the mathematical world, each one should be backed up by its own calculations, own justifications. So either in a spreadsheet or you can do your hand calculation. So whatever area you are assigning to the rod element, that needs to be highlighted very clearly. So and should be calculated. And then moving on to the fuselage frames. Fuselage frames more or less same like spar. So again it will be modeled as a combination of 1D and 2D. And then attachment and the linkages, those will be modeled as rigid elements or sometimes spring elements depending on the situations. Whenever it is small brackets attaching to some lug or something using a pin bolted or fastener, then it might be a spring element. Or then if it is a series of attachments on a bigger lug, such as horizontal stabilizer, which is on the horizontal stabilizer or vertical stabilizer, then it might be rigid body elements, MPCs, that will be used for modeling those attachments and fasteners. So if you want a better visualization, I would advise you to go to lecture 1 of this course, where I have provided some of the pictures for the aircraft wing interior structure and aircraft fuselage interior structures. If I am going back to 1, you can see that the spar is of more or less like a beam. So the with the flanges modeled as 2D elements, and the intersection between the flange and the web will be modeled as 1D, or sometimes the entire flange is modeled as 1D element with the web modeled as 2D element. Even within the 2D elements, sometimes the web for the web they will use only the shear element. That means it takes only the shear, it doesn't take any bending. The bending is primarily taken up by the flanges or the bar elements that is being modeled, or the rod elements, which is the couple, tension and compression, equal and opposite couple, that will be taken up by the rod elements. So it is the purely the decision of the FE analyst to how to accurately idealize the structure into a mathematical model, and just by the years of experience, an analyst can do it without any trial and error. So moving back to class 2 lecture, you you have a scenario over here where an aileron is attached to the wing. It is attached to an lug, which will be like a tuning fork, something like that. A lug which attached using a fastener, bolted. It's a bolted joint. So in the mathematical world, so this is meshed using 2D elements and combination of 2D and 1D wing. And similarly, aileron is also of the same sort, which is like a miniature wing. And this attachment lugs are modeled using a spider elements, which is the rigid elements, and then the bolted connection itself is modeled using a spring element between these two lugs, which is which is idealizing that these two lugs are being bolted together. So the user has to specify the shear stiffness and axial stiffness of the bolt. He has to calculate the based on the bolt geometry and bolt spec, fastener spec. He has to calculate the axial stiffness and the shear stiffness, and then need to feed those values into the tool. And at the same time, you should for the spider elements, for the rigid elements, you should know what degrees of freedom you should allow, what kind of movement it is allowed for the aileron, and then how the wing is attached, how this connection, how the interface point of the wing to the rest of the aircraft structure is being done. So he has to idealize. So on these idealizations, whatever that is being done, your model will be more or less accurate to the real structure. The poor idealization results in a model being inaccurate, and obviously the results from the inaccurate model would also be erroneous. Similarly, we have a stiffened panel, which is you can idealize at a fuselage frame, something like this, where you can see that some portion of the flange and the web cap being idealized as 1D element and the rest are idealized as 2D element. Over here, there are two different variants presented. I have modeled this one as completely with the Z section completely as 1D and with the flanges as 2D, and over here only the flange and the web as 2D and the intersection between them is modeled as 1D. So both could give you some results that might be reasonably close. This, but the situation of the or the applicability of this might vary. This will be used in a much bigger global model, but whereas this one would be the localized wing model or localized frame fuselage section model. Suppose if I'm using the if I'm modeling the whole aircraft for the which is like a loads model, then I would go for this. And whereas this one, if I model only the particular wing section, I would go for this. So in order to understand the internal forces and internal reactions, I need little bit more accurate model, which is this one. But in terms of the global forces, I just need to understand the loads at the aircraft interfaces, whole aircraft. Then my region of interest is not the wing or anything in particular, then I go for this. So moving on to the next slide, I have put a typical list of FE elements that is available within the Patron library, and then I have put some real-time examples how this is being idealized. So first, looking at the list of elements, we have zero dimensional element, which is 0D, which is like a point element, which is called mass element. So mass elements are the ones which it is used for adding mass. Suppose imagine there is a, you have a cantilever beam, and then I will go into paint now to demonstrate. Switching on to the paintbrush, imagine you have a cantilever beam and you have a dead mass over here on the cantilever beam. So how I can idealize this one into the FE? I can model the beam with various different elements, like it has two nodes, like connection of various different elements. And then I am arresting this node, and I am arresting all the translations are 0 and all the rotations are 0. So all these 6 degrees of freedom, each node point in the FEM has 6 degrees of freedom, which is 3 translations along, translation along x, translation along y, translation along z, and rotation along z, x, y, and z. So there are 6 degrees of freedom that will be arrested since it is clamped. And coming to the dead mass, it's not a force, it's just a mass. So what I can do is I can model a rigid element and then model a mass element over here, which is a point element. What it will apply, it will apply a mass, something like weight. Okay, so the weight will be applied on the beam. So instead of force, you are modeling it as mass. Okay, so the weight will be mass times the gravity, 9.81. So mass times the kilogram. Suppose if your mass is 10 kilograms or 100 kilograms, so the equivalent force will be in mass times 100 in times the 9.81. So will be 98.1, will be 98.1 newtons will be applied. The software, while running the analysis, while solving the problem, will apply 98.1 newtons at those nodes. So similarly, we have some scalar elements. What do you mean by scalar elements? It is between two coincident nodes. You have to create two nodes at the same location and then model the spring element. Spring element is nothing but your same like your spring mass system. The spring which is in the spring mass system, it represents stiffness. You can specify stiffness along all the three directions, or you want to specify along any one, that is fine. So remaining two directions you can simply put 0 0. So it can be customized to give stiffness in any of the three directions. Mainly spring elements are used for modeling the bolts, fasteners and connections. And moving on to 1D element, we have different types of 1D element available within Patron and Astron. First one is C rod. This is the rod element, and cone rod, same like rod element but with the enhanced capability. And then C tube, which is modeling for the tube. It has a little bit of flexure, bending capability. And C bar elements, bar and beam are one and the same. It has both axial bending and shear capabilities, but the only one different is bar can support only the constant cross section, but beam can support variable cross section such as tapering. And C bend is the uh, something like an arc over here. What you can see, something like an element which is in the shape of an arc, which is used for modeling arcs mainly for civil structural purposes. And then moving on to 2D, we have quad elements. One is the linear quads and another one is higher order quad elements. As I spoke earlier before, like one is the P refinement, which is having mid-side nodes. Imagine quad with the corner nodes. Corner nodes will be 4 nodes. Suppose you have nodes in the middle of the quad on each of the edges, then it will become 4 plus 4, 8. So C quad 8. So which is the higher order quadrilateral element. Similarly for C elements, triangular element has 3 nodes. Suppose the each edge is having a mid-side node as well, then it will become 6. 3 plus 3, 6. And then quad R element, and tria R, shear R. These are little bit rigid element in terms of stiffnesses. And then 3D elements, we have hex, pent and tetra element. And then there are some axisymmetric elements as well, which is higher order triangular elements and quad elements. And then finally the rigid elements, which is the spider elements. So we have R bar, which is something like bar but it's a rigid element. And RBE2 and RBE3, which is a typical spider element. RBE2 is mainly for the modeling the lugs, brackets, shear clips and those kind of stuff. And RBE3 is the interpolation element. And RSCon, so some RSCon is mainly for the weld, and R bar is also for the weld and those kind of very high rigid applications. Moving to the examples on the right, you can see that there is a very big strut. This is the picture is the real aircraft structure, which is the interior of the aircraft structure. You have a cabin monument where the food is stored for the passengers, and those are composite structures. And these monuments are something like your wardrobes in the house, but it will be attached to the aircraft ceiling on the top side, and the bottom side it will be attached to the aircraft floor using some sort of fittings, specialized fittings. On the what you are seeing is the top attachment, where you can see that this is a top panel and there is a beam running throughout the length, which is a steel beam or which is the machined aluminum beam. And there is a series of struts, and then finally this strut which is going from the side struts will be attaching to the aircraft interface, which is the on the ceiling of the aircraft there will be a lug. The other end of the strut attaches to that lug. So how this is being idealized in the finite element world is a series of spider elements, and then finally this strut is idealized as the rod element, C rod, and then finally this the node to which the aircraft attachment is made is arrested, is completely constrained for all 6 degrees of freedom. So this is just to show an example how the idealization has been made. Similarly, there is a situation over here. We have we have two panels that is meeting with an customized machined section beam, and how it's being idealized. You can see for this panel elements you can idealize it as a 2D element quad, and then this can be idealized with the rod element or bar element depending on the capability you want. Either if you want the axial and bending capability, you can go for rod element. So moving on to the next slide, we have some of the idealizations and some of the equations over here which I have put in just to show you how the what kind of forces or what kind of loads each of these elements take. First one is the simple 1D element, that which is the rod element. It takes only the axial forces. And next one is the typical skin panel element, which is a plate element which takes both axial and it could take bending. It takes bidirectional axial loads, and this is a shear element or the typical shell element which takes only the shear force. It doesn't take any force. It takes only the reacts only the in plane shear. And then moving on to the example which we previously saw, this one where an aileron is attached to the wing. So the lug on the aileron side is being bolted onto the lug on the wing. So you see how the connections made. So in between them they have two coincident nodes, and between those two coincident nodes there is a spring element that is being created. So depending on the direction of the creation of the spring element, the forces what you get as a result will vary. So if the spring if the coincident nodes are in the same plane, and also it depends on the how the location of the nodes are there. So if they are in the same plane, then you get an equal and opposite force, but if they are little bit vertically aligned, you get the vertical force, you don't get horizontal force. So clearly that indicates there is some error. The user might make made any mistake, and finally it will be realized only after the post processing done. So similarly the equation for the spring element is this one. It is the difference between the displacements times the stiffness. And over here what I have put is the T section, which is the flange and the web intersection connection, whereas the flanges are modeled using the 2D elements and web is modeled using 2D element, but the connection between them is modeled using a rod element. And these are the internal forces or the free body loads. When you take a cut section in the middle of a beam, you get the free body loads, So similarly, there is a free body elemental loads that is being shown here. How it is being calculated, you can see the force from the rod elements and also force from the each of those flange elements and forces from the web elements. The total force on the total force on one side is the total force divided by 2. So moving on to the next slide, I have put some the global finite element model of an fighter jet, and then how the localized structure would look like. So imagine this is a global model which you are modeling into the FEM. So you don't have any particular area of interest, and then you just want to run the model to check the loads at the interface points, which is the connection points. And then finally, from the using the loads from the global model, you want to run some local analysis on your wing, on one of its wings, and you have to little bit make it finer, the mesh, and then little bit put in some more detail. You have to little bit model the attachments and run the wing alone in order to get the stress distribution on the wings. And further to this local model, there is you are further investigating one of the attachments of this wing to the fuselage. So this is still further local stress model where your fasteners, whatever you have modeled it as spider elements or something, that is being modeled properly in three-dimensional, using three-dimensional elements, and then the contacts between the fastener and the lug is defined, and your area of interest is this local attachment only. So in such case, more and more finer mesh and more and more higher order elements and capabilities will be used just to accurately represent the stiffness and then to extract the results. Over here you can see that a simple stiffened panel with plate and beam, that is being how it is being idealized as we discussed earlier in a couple of minutes back. So you can see the global model over here where it is not these both these images are of a global model. Those are not much detailed enough because most global structures or global models are run only to extract the loads at their interfaces. So whenever the global analysis is being done, so the local analysis or the local points are of no interest. So and whenever the local analysis is being done, so much detail is being put into the model in order to understand, in order to investigate the transfer of forces between the parts. Sorry, I'm okay. Now moving on to the types of connection elements. Why I have put this topic as a separate is this is really important topic, and each and every user needs to understand the importance of these connection points, because basically your connection points are the points where you apply the boundary conditions or sometimes loads. So that is going to have a very huge impact on the model. Mistake done on the connection points will completely spoil your model. with the results being completely wrong. So one has to accurately represent the model. So the FE model of the fastener joints, if you look at, they have a couple of categories. One is fasteners and other one is plates. Sometimes it is being modeled using the fastener elements, which are typically the beam elements, spring elements, and in a very rare case sometimes using solid elements, sometimes using plates, solid and shell elements. This is mostly in the local model, not in the global model. Mostly in a bigger or global model, the fastener joints are modeled using a beam elements, spring elements, or rigid body elements, which is the connector elements. Again, the connector elements, it might be a bush or bushing and fastener, those type of connector elements. So for all these types of connections, which is the fastened connection, over here what you are seeing is the riveted connections. Yeah, aircraft skin panel riveted to the spar, which is the Z section spar, and the rivets, these are rivets, riveted joints. So these kind of connections that is being modeled, these will be modeled as a Scalar element, which is the spring element, and C bush element is one and the same. Bush is also a spring element. There is nothing different, just only the way the element has been defined. So in terms of properties, so other than that there is nothing different. So for these connections and for these type of connections between the skin panel and the stiffener, so one has to define the stiffness at those connection points. As I mentioned earlier, these stiffness and whatever values you define should be backed up by calculations, engineering judgments. So if you look at the connections, this is being done using Hertz formula. So this Hertz formula is used for calculating the axial stiffness and the bolt shear stiffness, which is for mainly for the bolt flexibility. So in that way, then you can accurately represent the connection between the skin panel and the stiffener. And finally, the skin itself is you have to come up with the geometrical parameters, area and the moment of inertia. Similarly for the stringer or spar, whatever it is, you have to accurately calculate the area and the moment of inertia. For most of these geometries, drawings will be provided in a typical aircraft industry scenario, where you have to pull out the dimensions from the drawings, and then what type of fasteners that is being used, and in terms of fastener specs, and you have to use the engineering manuals or engineering handbooks just to work out the bolt flexibilities, both axial and shear stiffnesses, and then feed in those values into the finite element tool to accurately represent them. So to give you a very quick recap, so the user has to accurately represent the model by using the engineering judgments, proper engineering judgments, and idealizing um, with the suitable elements in terms of load capabilities, in terms of behavioral aspects. In that way, the stiffness of the real structure could be accurately captured. Thank you very much. I'll see you in next lecture, class 3.